So let me come to the class 5. Here in the class 5, we are measuring the inductance. So how inductance is measured is being taught in class 5. So first, the measurement of inductance using Maxwell's inductance capacitance bridge. Here, Maxwell's bridge can be used to measure inductance by comparison either with a variable standard self-inductance or with a standard variable capacitance. These two measurements can be done by using the Maxwell's bridge in two different forms. So first one is Maxwell's inductance bridge. Using this bridge, we can measure inductance by comparing it with a standard variable self-inductance, which is arranged in the bridge circuit form. But in the syllabus, we have here the Maxwell's inductance capacitance bridge. So I'm going directly to the Maxwell's inductance capacitance bridge. Here, this diagram shows Maxwell's IC bridge, that is inductance capacitance bridge. Using this bridge, we can measure inductance by comparing with a variable standard capacitor. The bridge circuit, it's shown here. One of the ratio arms consists of resistance and capacitance in parallel. Hence, it is very simple to write the bridge equations in the admittance form. You can see here what are the inductance, what are the parameters is given. The general bridge balance equation is Z1 into Z4 into Z1 into, you can see here, Z1 into Z4, which is equal to Z2 into Z3. So when I do this, Zx is unknown impedance is given by, which is equal to Z2 into Z3 by Z1. Here I have written what you're saying, that Z2 into Z3 into Y1, where Zx is equal to Z2, Z3, Y1. Y1 means admittance 1. So admittance 1 is equal to 1 by Z1, that is R1 in parallel with C1. Now Z2 is equal to R2, Z3 will be equal to R3. So Zx is equal to Rx plus, you can see here, Zx is equal to Rx plus j omega Lx, as Lx is in series with Rx. You can say, look at the diagram, students. So admittance 1 is equal to 1 by R1 plus j omega C1. So Z1 is equal to, since Z1 here, R1 is in parallel with C1. So take the parallel. That becomes, because 1 by j is equal to minus j. Rx plus j omega Lx we have to find. So similarly, we have to equal real parts as well as imaginary parts. When I do that, I get the equation finally Rx is equal to what? R2 into R3 by R1, whereas Lx is equal to R2, R3 into C1. You can see here. So how did I get? So first R1 plus j omega Lx is I got Zx, and then again I simplified further and equated real and imaginary terms, and I got Rx and Lx. So the resistance are expressed in ohms and inductances are expressed in henries. Capacitances are expressed in farads. The quality factor of the coil can also be found. That is nothing but Q is called as quality factor, which is equal to omega Lx by Rx. So you got Lx as well as Rx. Substitute. Finally, we'll end up with Q is equal to omega R1 into C1. This is about Maxwell's inductance bridge. So here, this is the phasor diagram. So the phasor diagram, how it can be written? It will be by taking the current as a reference, and we have to take the IC and IR1 as the phases. The resultant of this will be I3. This is I3. The IC, when it is added with IR1, you will get the current I3. This current is equal to I1. So now this same way, when I do that on the same phasor, you get V4 or V3. So you can see here, this from here to here, from the origin, it's V4, which is equal to V3. So the resultant is, when this is added with the E3, that is here, then the resultant, this phasor, when it is added with this phasor, you get the resultant voltage, that is E. Okay, either you call it as E or you can call it as V. E is the R, here E3 or V3, V1 or V2. Like the E1 V2 is equal to V1 V2. Anything you can call. However, the naming convention can be done however you want. But the phases, whatever you have written there, that should represent here in the phasor diagram. So what are the advantages of using the standard known capacitor for the measurement? What are the advantages here? So we will see that in a Hayes bridge, what are the advantages? Sorry, Maxwell's bridge. So the advantages of this using standard known capacitor for the measurement is the capacitors are less expensive than stable and accurate standard inductors. So capacitors are almost lossless. That's right. And one more is external fields have less effect on a capacitor. The standard inductor requires well shielding in order to eliminate the effect of stray magnetic fields. One more advantage is the standard inductor will not present its rated value of inductance unless current flow through it is precisely adjusted. Finally, the capacitors are smaller in size. This bridge is also called Maxwell-Wien bridge. So after completing this, we understood what are the advantages and disadvantages. So coming to disadvantages, so you can list there. There are 4 disadvantages what I have listed here. So variable capacitors used, it is little expensive, and how it can be done. That it cannot be used for this Maxwell's bridge cannot be used for the measurement of high Q values. Its use is limited to the measurement of low Q values from 1 to 10. So this can be proved from phase angle balance condition, which says that sum of the angles of one pair of opposite arms must be equal. That is, theta 1 plus theta 4 should be equal to theta 2 plus theta 3. But theta 2 and theta 3 are 0, as the corresponding impedances are pure resistances. So for high Q values, the angle theta 4 is almost 90 degree. Hence, theta 1 must be minus 90 degree. But theta 1 gets decided by parallel combination of R1 and C1. To get theta 1 as almost minus 90 degree, the value of R1 should be very, very high. So practically such high resistance is not possible. So hence Q values, high Q values cannot be measured. Second disadvantage is there is an interaction between the resistance and reactance balances. So getting the balance adjustment is little difficult. Okay. So it is next one is it is unsuited for the coils with low Q values less than 1 because of this balance convergence problem. So final disadvantage, what I can say is the bridge balance equations are independent of frequency. But practically the properties of coil under test vary with frequency, which can cause error. Commercial Maxwell's bridge measures the inductance from 1 to 1000 Henry with plus or minus 2% error. That will be there almost always. So that completes class 5. And we have discussed we have completed the Maxwell's inductance capacitance bridge as of now.